This podcast is supported by Hannover Messe, your meeting place for the industrial community.
Hi there, welcome to a new edition of the Industrial AI podcast. My name is Peter Seeberg and I'm your host. Today I'm going to be talking to Frank Hutter. He's professor and co-founder at Prior Labs. And Frank and I are going to be talking about TabPFN, more specifically applying TabPFN for tabular and for time series data. Hi, Frank.
Hey, Peter. It's awesome to be back on the show.
All right. Good to hear. Please introduce yourself to our listeners, Frank.
Yeah, hi. I have been a professor for machine learning in Freiburg for the last 10 years. Before that, I was in beautiful British Columbia and Vancouver for 9 years. And then all that time, I've been working on automated algorithm design. In the last 12 years, focusing more on machine learning, doing automated machine learning, AutoML. So I co-founded the workshops on AutoML at ICML. We ran those for 8 years. And then 3 years ago, we transitioned to a conference on AutoML that has been very nice and successful, and a growing community that's really a community of friends. It's really nice. Been building that over the years. And then all that time I've been wearing the academic hat. And we've been building AutoML systems and also had the first MOOC on AutoML, the first book on AutoML, and won the first competitions on AutoML back in 2015, 2016 with AutoSQLearn. And that was already a great startup opportunity. Back then, it was like state of the art, really making things easier for tabular data. And had we been in Silicon Valley, I think we would have had a startup back then and ended up not doing that. But over the last couple of years, I've been definitely feeling that we need to be more out there in order to bring the great technology that we develop actually also to everyone. AutoML always was about democratizing machine learning and bringing it to everyone and making it really easy for everyone. And I think we've been stuck in our ivory tower for a little too long. And like having a business, you actually have a much bigger motivation to really make your customer happy and make everything easy for them. So that was one motivation for actually now going out and also founding a company. And the other motivation was that we just have a killer product with TabPFN, or killer technology that we can make into a killer product and can really make lives better for a lot of people and can help the world hopefully make better decisions on the tabular data.
Thank you. Great introduction, Frank. Today we're not going to talk about AutoML. We have done that. Actually, it's just a week or two ago that Robert did an interview again on AutoML. You and I, we met, it's about 2 years back, I guess, at our Industrial AI conference that was with Arburg at that time. You, some of your PhD students, Samuel Miller was there, Noah Holman, I recall. We did a lot of AutoML, but you also introduced already at that time and ran a track on TabPFN, where you also announced that you were looking at ways to get technology into the hands of the users. Meanwhile, as you said, we'll come to that later on, you founded a company and you had TabPFN published in Nature Science Journal. To start with the latter, getting content, I guess, into Nature, one of the world's probably most read, most prestigious academic journals, is quite an achievement, I would say. So congratulations.
Thank you very much. It still blows my mind that this worked. We had the audacity to try, and it did work. You have to shoot high in order to succeed sometimes. But really, when we submitted the first paper on TabPFN, this was 2 years ago, we submitted to iClear, and the results were just so amazing. It was like within a second being better than AutoSQLearn would be in 4 hours, and probably you could run AutoSQLearn as long as you want, and it wouldn't have gotten as good. And AutoSQLearn already had like probably 10 person years under its hood, and TabPFN at that time like maybe half of a person year, and it already was so strong. And I really knew, hey, this is something that can be a breakthrough. and that can really change a lot of things. It had a lot of limitations. That's why there was still a lot of room for paper afterwards. But after we submitted that first paper, I was like, if I was at DeepMind, we would have sent this to Nature. But then it was already out and it was submitted, and at iClear, even if you retract the paper, it's going to stay online. And so it was like, well, we didn't retract it. And it almost got rejected because, iClear doesn't care about Tabula, and the results were too good. So the reviewers were quite skeptical. But really, I mean, while we saw a lot of potential in there, and while I really thought this is a breakthrough, it wasn't a breakthrough in terms of impact. It was super strong on a very limited type of data, namely numerical data up to like very small data sets, up to 1,000 data points, no outliers, no missing values, no imbalance, no nothing, like none of the stuff that you have in data science. So that is what we've been basically heads down building for 1.5 years to just really get rid of all these failure modes and develop something that we wanted to be the new default for small-ish tabular data sets. So this is small up to 10,000 data points now and 500 features.
Yeah, let's jump in there. So you already did the introduction. I'm not going to go back. You just did that to the original paper that was called Transformer, that solves small tabular classification problems in a second. I guess you could call that version 1 maybe.
Mm-hmm.
And then the Nature article, TabPFN, I guess you could call that version 2. Is that correct?
Yeah.
Right. Accurate predictions on small data, as you say, with a tabular foundation model. Now, from the latter, because that's what I got through, that's what we'll use here as what we're going to be talking about. Maybe first tell us about tabular data. What are they? I do believe that probably 100% of our listeners, every now and then, some of us a lot, many hours a day. Some of us just use them without knowing them, by just looking at Excel data. I assume we are using tabular data. So how important is tabular data in general in the world of data scientists today?
Yeah, so tabular data is indeed, it's probably still the most widespread type of data in the enterprise. I just think Excel spreadsheets, think relational databases, numbers stored in structured format. There's a lot of that. And it's pretty much in every aspect of research and industry, business that you can think of. So like, for example, like healthcare, in the medical sector, there's all kinds of different types of data sets about patients, about diseases, etc. Finance, business analytics, insurance, telecommunications, retail, energy, like marketing. It's just everywhere. But maybe to make it a bit more specific, so there's these classification and regression problems, there's time series problems, there's recommender systems, and all of these are sort of at their core tabular. And if you drill down into maybe healthcare, so healthcare is this huge field, but even within healthcare, you could do personalized risk prediction or drug response prediction or clinical decision support or readmission statistics, etc. And drilling down maybe even further into one of them. So if you want to, for example, predict based on some blood markers, like you have some omics values from the blood, like proteomics or metabolomics or genomics or whatnot. And so you have some numbers from your blood values. And from that, you can predict all kinds of things. For example, whether this patient has early stage Alzheimer's. Well, you could just wait 5 years and see, then you know whether they had early stage Alzheimer's, but then it's too late to treat it. But so data collection is actually easy. It's easy to collect this historical data. Like for previous patients, you know whether they had it or not, but you want to predict it for the current patient right now. And so that's a tabular data set. You have like maybe 5,000 patients. For all of them, you have the blood markers. You know whether they had early stage Alzheimer's at the time or not. And then you have a new patient where you have the omics blood markers and you want to predict, do they have it or not? So that's a binary classification problem. There is also classification problems where you have more than 2 classes, maybe 3, 4, 5, 6, 7, or 100. And then there's regression problems where you want to predict a number. For example, what is the stock price going to be tomorrow, etc. So there's really, the sky's the limit for tabular data, and the methods we use are really 20 years old. So gradient boosting is the typical type of technique that people use, and the first publications on that are sort of from the, I think 2002 or so, and then XGBoost is maybe 12 years old or so, and that's really what everybody uses. And this whole revolution of deep learning that has really dominated the modern machine learning has taken place in vision and speech, and then more lately in text, of course, with ChatGPT and co. So now we have these foundation models on text, we have foundation models on images, but we don't have foundation models on tables. And rather, we did not have. Now we do have one, namely TabPFN. And I guess we will get to what it means to be a foundation model in a little bit. But in a nutshell, it's you're pre-trained on a whole lot of different data, and then you can do well based on small individual input. So we've pre-trained on millions of data sets to do well on small data sets, to basically learn the statistics behind tabular data. And we learned a tabular classification or regression algorithm from the data. And being a foundation model also means something like you can fine-tune it. Like you can download a llama and you can fine-tune it to your company data. Just like that, you could download TabPFN and fine-tune it to your data, and it would get better on your types of data. And you can't do that with an XGBoost. With XGBoost, it runs fresh on every new data set you give it. And so especially if the data set is small, it will typically overfit. And with TabPFN, we've learned not to overfit.
Very good. Well, you gave in more detail the example of the medical environment. It does apply in the same way as we are the Industrial AI podcast for industrial as well. I saw you've used, you looked at a faulty steel plates. I saw Mercedes-Benz test bench data set. Now, I must say, as long as I was involved kind of directly in the data science of the industrial environment, I have been all the time involved in the time series. We come to those later. But nevertheless, my feeling was that even in the industrial environment, and with the examples that I just gave, is in that environment using the tabular data more like, let's get these test results, almost like similar to a human being, I guess. Let's look at the blood, let's look at the pressure, etc., etc. And then afterwards, we're going to jump into and see what has been happening, as opposed to if we then know and understand this data and know which the features are that maybe in this case specifically make the production line stand still because of a certain combination of values, then we would probably try to use it interactively, like in a time series environment, right? So because then we can say, okay, now it happens. And that means that in, 10 minutes or 1 hour or 1 day, the machine is going to break down.
Yeah, absolutely. If you have such a predictive model, then you can, of course, also look into what if I change this value? What if I change this value? How important is this particular feature in order to predict the future? How important is this particular blood marker? How important is this particular, coefficient or this particular surface roughness or whatnot? Like it's this black, I was going to say black box, but it's not actually a black box. It's a generic interface where you can just feed any type of data, and it just applies to any type of data, to the medical domain, to the industrial domain, etc. And it's the same algorithm that applies on the meta level, and the same interpretability tools that apply on the meta level that tell you then how important is each of these individual features.
Now, you said a little bit about how it works. You did a comparison with XGBoost. I understand you outperform any of these previous methods concentrating on data sets up to 10,000 samples. And then I've been thinking, what does that mean, 10,000 samples? I mean, the one that I would use to have a lot less, but then looking at industry, looking at all these different use cases and markets, nevertheless. And then I thought, well, maybe still you represent whatever, 80% of, and then I saw specific numbers. So can you give us an idea on that? What does that mean? What percentage of the total potentially available market would that be?
Well, I mean, in terms of publicly available data, that's sort of high quality on OpenML, on the public open machine learning library repository. So there, about 70% of the data sets are 10,000 data points or less. If you want to think in terms of time series, if you, for example, think you have one timestamp every day, then you have 365 timestamps a year. So then you could go back 30 years. If you have hourly timestamps, then it's more like a year and a bit. If you have quarter second timestamps, you're not going to get very far with 10,000 data points.
Okay, that's a very good point. Yeah, I was going to come to the time series later, but as we're at it now, that's perfectly fine. Okay, so as I was going to ask, because, well, many times we don't have, well, we do have the second, but we go further down to the millisecond. So going down to the millisecond, maybe your answer could be yes, it would work the same way as others. That is the question. But you already implicitly say the limitation for the moment would be that the total can only be, what did you say, 10,000. So if we go to the millisecond is already 1,000, then we could have only, which could still in certain cases, but it would be then be limited to 10 seconds.
Yeah, I mean, if you need a resolution of a millisecond, then probably there are not that many processes where you need more than 10 seconds of data. But if you both need really long sequences and super high frequency, then we can't. Well, we could do it with the current TabPFN, but like the claims that it's really strong, they have only been validated up to 10,000 data points and 500 features. And we do hope that this is not a limitation that will remain, but that is a current limitation.
Okay, nevertheless, you said something really clear in my brain here, and I'm not certain the way you put it. Maybe again, looking at that complete potential of both the frequency and then the total time you need. In my brain, I go back and know that we've been looking at a year's or two worth of data. But yes, I cannot confirm. I would agree, probably not believe that they were actually milliseconds. They were probably more like seconds or even hours type of data. Okay, very good. One topic I've seen is the concept of in-context learning. Can you share that with us, what that means exactly, what role that has been?
Mm-hmm. Yeah, so in-context learning is a term that was coined in the GPT-2 paper, where they basically... So it is a concept that comes from natural language processing. And in natural language processing, there's two types of learning mechanisms at play. There's one that's called in-weight learning, which is your standard type of learning. And then in-context learning is something where you actually look at your context window, so at the prompt, and depending on a prompt, you execute different algorithms. So for example, in the GPT-2 paper, they had an example where they said, I don't know the exact example anymore, but one where it's basically is dog, Hund, mother, Mutter, father, question mark. And from that, the system would infer, aha, I'm supposed to translate from one language to the other. Or you could have a spelling correction task where it's like some misspelled word and maps to the non-misspelled word, and three, 4 examples of that. And then it learns, aha, I'm supposed to function as a spelling corrector. And so these early days of language models actually getting what we want them to do, that comes from in-context learning. And so it's basically a similar mechanism is at play for us, because we feed the entire data set. So that's where the limitation comes from. the entire up to 10,000 data points we feed as context to the network, do a forward pass in order to predict the Y values, so the classification or the regression values for the test data, which we also feed in as input. So we feed our entire training data as part of the context, and then the features of the test data points, and the output should be the predictions for the test data points. And that is the training signal that we gave it over millions of data sets. So millions of data sets we generated. And for each of these generated data sets, we learned to actually, we predict something. That test prediction is different from the true test prediction. And the difference between these, we have a loss term on there, and that loss is going to be minimized. And if you minimize that loss over millions of different data sets, then it gets smaller and smaller and smaller, just like is normal with stochastic gradient descent. Now, so one data set actually plays a role of one data point in normal SGD. So it's a type of meta learning. We learn an algorithm, and that algorithm takes as input an entire data set and then outputs the predictions for the test points. And it learns to output them as close to the truth as possible.
Now, I understand that your data sets are based of synthetic data, right? So what is synthetic data? How can you make sure in general that synthetic data represents the world around us as it is, or at least as we conceive it, so to say?
Yeah, a very good question. Like there's pros and cons of synthetic data. One potential con is, we need to also generate synthetic data that is really similar to the true data. One big benefit is that we don't have the situation that GPT has, where you train on the entire internet and then there's garbage in, garbage out. For us, we just really very clearly can say, this is the type of data that we wanted to work well on. These are the types of patterns it should pick up, and then it will pick up these types of patterns. So for example, we could say, I expect to see only linear slopes for a regression task where you have y equals a times x1 plus x2. So you have a y-intercept and then the slope. Those are the two variables that you want to predict. And you always you know it's going to be a linear function. Then we're going to sample millions of linear functions and you're going to train on that. And the predictions that will come out will be linear functions. That is great if we know that it's going to be a linear function. But if it's not a linear function, then, we're still going to predict a linear function because our prior said it's going to be a linear function. And so that's a misspecification of the prior. There we should have had a more general prior that encompasses the true types of patterns that are in the data. And so really a lot of work has gone into these synthetic data generation pipelines in order to generate the types of patterns that do exist in the data. And basically what we have used is the principles from causality. So when we have a tabular data set, typically it is the case that there's some types of causal relationships in there. Some features cause some other features. Some features maybe cause the prediction variable. Maybe the prediction variable also causes some of the features. We don't quite know how these causal relationships are going to go. There's also going to be some independence. There's going to be some features that bear no meaning whatsoever, and they're not connected to any of the other features. All of this is possible, but we don't know ahead of time which of these situations is the right one. But given some observational data, some of these become more likely than others. So you can think of TabPFN as actually looking at millions of possible causal explanations of the data at hand and building the Bayesian integral over these millions of possible causal interpretations. So each of these causal interpretations would make different predictions, and each of them has a different probability based on how likely that causal prediction is given the actual data at hand. Now that sounds ludicrously inefficient, doing a Bayesian integral over hundreds of millions of possible causal.
I wasn't going to say that.
But that was just a training signal. So the transformer has learned to approximate that training signal. It doesn't have the capacity to remember hundreds of millions of data sets in there. It's actually a pretty small transformer with a couple of dozen million weights, not trillions of weights, not billions of weights, but really just a couple dozen billions. So with a small capacity, it can still learn to approximate this training signal. But in order to do that well, it needs to generalize. It needs to generalize over these different types of cases. And in doing so, it also generalizes to new cases. So one example that my PhD student Sam just came up with is where he had as a prior either a linear slope or a sinusoidal function. And at prediction time, we actually had data sets that were a sinusoidal plus a linear function. So a trend plus a sinusoidal on top of it. And actually, TabPFN could just fit that beautifully. And so I kind of like to think of it as the prior capturing the basis functions of what are the patterns that we want to map somewhere, and then we learn to combine them in the right way.
Okay, interesting. So how do you make it available to the public? Is it closed source, open source? And also, I see you're releasing an API to use your GPUs to compute for third parties. What's that about?
Mm-hmm. Yeah, so it's a very open release. It's an Apache license, just with a small enhancement, namely an attribution requirement that comes from the Llama license. For Llama, you had to say Meta's Llama model. You had to say built with Meta Llama, and for us, you have to say built with TabPFN. And the reason for that is we just really want distribution in the community. We want everybody to know about TabPFN and want people to really rally behind it. And there's these people who love XGBoost and will defend it and use it for everything. And we want to sort of build up these folks who also feel similarly about TabPFN. And so we just want the world to know about TabPFN. And it is sort of an uphill battle. AutoML was already very strong for a long time, giving better results than XGBoost in many cases. But still, XGBoost is sort of typically used. And we just really want to spread this, the word to spread. And it's a good way to say, well, people have to say built with TabPFN, then other people see, hey, there's this TabPFN thing. Let me also try this out. So that's the one thing. It's an open source, open weight release. And the other component is it's particularly good if you have a GPU, but we don't want to limit it to those users who have GPUs. We also, as a convenience feature, we also offer an API. And if you upload your data to that API, then the compute runs on our GPUs and we make predictions for you, and you don't have to own a GPU and still get good results quickly.
Sounds great. Let's move into a little bit more detail on the time series. So just before your Nature paper on tabular data came out, you just launched another paper at the Understand NeurIPS time series workshop. In your announcement you did on LinkedIn, I believe, you seem to be very surprised. You say, it's crazy that this works, quote unquote. That what had worked on tabular data also seemed to work on time series, which reminded me very interestingly something similar that happened with XLSTM, which they were concentrating on language. And then similar, I believe, to you guys, there was a PhD who said, okay, let's try it on images, and it worked as well. Tell us about it, how that came. So the paper is called the Tabular Foundation Model. TabPFN outperforms specialized time series forecasting models based on simple features.
Yeah, so it's very much like the title says. It is the same model. It's exactly the same model that we use in the Nature paper for regression. And we, in particular, my master's student, Liam, he basically featurized time series. So like a time series, this is univariate time series, that's where there's been quite a lot of research on foundation models. So univariate time series is basically for each timestamp, you have a value. And then you just have this one signal that changes over time. And you can cast this as, well, each timestamp, you can say, well, this is a time of day. This is a day of the month. This is a day of the week. this is a month of the year, etc. So you can basically create these features from it. And then you can also, for any time in the future, for example, like 5 hours in the future, or 5 days, or 17 days, or whatever, you can compute, well, what time of day is this going to be, what day of the week is this going to be, which day of the month, etc. Then you have these features, and you just put these features, so that the training data is going to be your time series so far and its featureization, and the test is going to be the point in the future where you want to predict the featureization of that. And then the question mark to predict is, well, the signal at that point. And he just put it into TabPFN in this very simple representation, and it directly actually worked better than the best time series foundation models. So foundation models specifically trained in order to do well on time series, foundation models trained on many real world time series, etc. With lots of data augmentation tricks, also other extensions or follow-up works of our first PFN papers and TabPFN paper. There had been extensions to forecasting. People had already simulated time series data and had some priors for time series data. But this new model doesn't have any of that. It has never seen a real data set, and it has never seen a time series, and it has never seen the particular featureization we used for a time series in order to make it a tabular data set. And nevertheless, it just works out of the box. It still blows my mind.
Yeah, well, I was going to ask you as well exactly that, because that's what I'm not used to, so to say. So I do not need to pre-train it, as you say, out of the box. I download it, I use it, I start it, and it works.
Yeah, that is a surprising thing. I am confident, we have not done it yet, but I am confident that when you fine-tune it for time series data, when you fine-tune it for this particular type of featureization, when you fine-tune it on your own company's data, on your own industrial data, it will get better for that. But we haven't done that, and it's still actually just very recently, it also got #1 in this most popular benchmark these days, Gift Eval, that was where Kronos was the best, Amazon's Kronos. And so we just took #1 in the leaderboard there this week. And with the same model that's in the Nature paper, and no changes.
I saw that. Yeah, it's amazing. Now, you say you haven't done yet. Let's move into your company. You founded a company, and then at the same time, you tell us what it is that you want to be doing. Then you haven't, I feel although it's already mind-blowing, there is still potential in certain directions. So let's spend the third of our discussion on exactly that. So you founded Prior Labs. What is Prior Labs about? And go back to the beginning, you kind of suggested maybe if you would have been in Silicon Valley, you would have already found it earlier. But now, nevertheless, you decided to found a company. What is Prior Labs about?
Yeah, so Prior Labs is the world's first company that is specifically focused on tabular foundation models, so models like TabPFN. And its mission is to actually help people to make better predictions with their tabular data, and thereby hopefully help make the world a better place, because the downstream predictions, the downstream decisions need to be better in our world. I think some people maybe don't extrapolate the future quite right and make some poor decisions, and hopefully we can improve that over time. But so maybe going back a little bit to your question about, in Silicon Valley, we would have probably already founded something in 2015, 2016. There were other startups. There was like one startup back then, the small company called Data Robot, that in the meantime then had this $6 billion evaluation. They did go down to 1 billion, I think. So I think not everything is trivial, even if you're there. But they were the first company that was really basically doing AutoML. And I had my academic hat on, and we never really interacted with that company. It's pretty sad. Like, looking back, I should have reached out immediately with my academic hat on and gotten them as keynote speakers and really forged a much closer interaction with industry, with this type of industry, with companies in the data science world. And I didn't. And therefore, for the longest time, there sort of we had this parallel existence of the academic AutoML world, and then the world of folks who actually build amazing products based on AutoML and really go the full last mile and make it easy to use, give people like easy ML ops, give people like a way to monitor how is this model doing and so on. So it's not just the machine learning part that most people don't actually find that annoying, but it's a data cleaning, the data pre-processing, the ML ops, the serving, the compute, so the whole infrastructure needed to be there. And that's where, that's what a lot of the startups in AutoML or like in tabular learning or data science have been doing. In the meantime, of course, there's also Databricks and Snowflake as giants in this space. And what we are trying to do with Prior Labs is really to build a horizontal model, like to build these tabular foundation models that can be used in all kinds of different types of systems. So you should be able to use them trivially within Snowflake, within Databricks, within DataRobot. And if we build a better tabular foundation model, then you just do a new pip install and everything is better. Just like if OpenAI comes out with a new version of ChatGPT or DeepSeek comes out with a new version, then you just directly have a better model and have impact on a whole lot of different applications where we want to sit deep in the application layers. We want to have people access it through the API, have people access through also language models, through Excel, through plugins, through all kinds of different means. And it's one model that is also serves all kinds of different businesses, from the medical domain. Well, not only business, also like public research and so on, but also different businesses, like the industry, the data science businesses, everything. And so we really want to play close to our strengths. We are really good at developing better models. And when we develop a better model, that should have direct business impact. And that's going to be the business model.
Until you have that horizontal model kind of available, interested parties can nevertheless contact you, or they can at the same time use your open source available solutions. And then when they run into problems or they need support, is that when they can come to you? Is that what you're for?
Yeah, absolutely. I mean, so right now, a lot of companies are actually already reaching out to us. We're dealing a lot with customer inbound right now because people know that we can build better models than we already have. And there are some companies also for whom the very free license we have with this requirement to attribute TabPFN is annoying. Like if you have like an API and you don't want to say in this API built with TabPFN, because I don't know, it's like some app people use and you don't want to have to display in this app built with TabPFN, but you still want to use it, then there's alternative licensing schemes where you don't have to say it. So even with this first version, there's people who want to use it under alternative licenses. But in the long run, we want to definitely have enterprise partnerships and work with many big companies to host our model on premise and help them get better solutions for their particular data. Maybe have some people on site with them, help them build better models for their particular application, help them use their wealth of expertise in order to build better models for them. And just have a lot of these really deep partnerships.
Sounds great. To get there, tell us about your team. Where are you based? Tell us about your colleagues. Are you looking for new colleagues? And if so, what should they bring?
Yeah, we just closed our first round of funding, and we have we haven't announced the round yet, but it's I'm really happy with the round, and we have a solid funding in order to hire top talent. And we're of course looking for workforce to do the engineering really well, like ML engineers, backend engineers, but then also a lot of people that actually know how to do research in a sense, but applied research to solve actual problems, like to scale our model up to larger data sets, to be faster in inference, to also, maybe get some causal understanding into the model, maybe making it promptable. So users can interact with it through language and so on. So there's all kinds of different challenges that actually are non-trivial. So you can't just say, hey, engineer, how about you program that? That engineer would first need to go and actually figure out how to do this, and actually do something that's not all that different from doing scientific research, except that, well, the focus will not be on maybe beating some random made up benchmark and getting the N plus first paper out, but actually getting great performance for the real world benchmarks and delivering great results for the customers and building great products. And we will continue publishing, but the focus will be on building amazing products. And then once we have an amazing product, we can publish something about it.
Great. Interested listeners can find the jobs on your website, right? Prior Labs.
Yes, exactly. priorlabs.ai.
All right. Okay, let's come to a close here.
One other thing I wanted to say, sorry.
Please do.
Use cases. So I mentioned we really do want distribution. We want to see people use us in all kinds of different applications. And I'm sure a lot of listeners are actually intrigued and are trying this. Please tell us. And we're really happy to amplify whatever content you create. If you write a blog post, or you tweet something, or you put something on LinkedIn or Blue Sky or whatnot, let us know, and we're happy to amplify that. We also have a repository with different use cases that we list. It's currently, this might change, but it's currently in our GitHub in Prior Labs. It's an amazing TabPFN. So it's one of these repos where you can just do a pull request. Hey, I have this use case, and link this blog post or link this paper, and so on. So we want to make it easy for the community to organize what has it been used for, and maybe, hey, there's a notebook already for doing customer churn prediction with TabPFN, and there's this notebook and there's this notebook. We really want to build this community of data scientists around TabPFN, and not only TabPFN, but really a community of data scientists, and understand what they need in order to actually then build better products for these people. And for that, please do get in touch. We have a Discord as well. And in the Discord, we do announce new stuff before it goes on social media. We have over 200 people already in the Discord. So it's definitely growing quickly, and would love for more people to join.
Most certainly. We'll share all that information in the podcast notes as well. Now, I'm going to close from my side, and then I'm going to ask you to just react on that. So the quote that you had a couple of days ago, I believe, is you said, you already mentioned DeepSeek. So you say DeepSeek R1 is a cheap, non-US open source foundation model challenging US market leaders, ... And so is TabPFN version 2. Now, at a very top level, very specific relating to TabPFN, but where are we standing? Artificial intelligence, machine learning, data science. Then we have had Gen AI, you talked about it. But for quite a couple of years now, you've been looking at the tabular data, AutoML, time series. You've been in the world, you've been working here in Europe. US, China, Europe. So this complete big picture, where are we standing today, and where do you see the major developments, as far as that is possible to foresee? That's what the business we're in, right? In the next couple of years.
Yeah. So sort of as usual these days, there's a really quick pace in development, right? There's DeepSeek as this open source alternative. to OpenAI, and this didn't grow from like since yesterday. DeepSeek has been a company that's been growing over the last couple of years, and now it made a big splash. This is not the only company that has been having success, or not the only open source player that has had success. Like even in Germany, actually, with the Lion initiative, Jenny Jitsev and Jülich, he had OpenClip like 2 years ago, actually matching the best language text models back then, the clip. And yeah, nobody cared in a sense. And well, LLMs, of course, have captured the public more so than language models, but language models, than language vision models. But language vision models, they're the basis for things like Stable Diffusion, which also comes out of Germany, like came from Robin Rombach back then in Munich, now having Black Forest Labs in Freiburg and having amazing open source software that is the best in the world for vision models that is promptable. And so now we have TabPFN, which is the best in the world, another foundation model also in Freiburg. I think we definitely don't need to hide. What we do not have in Europe or Germany are these mega companies. We don't have 10 billion, 100 billion financing rounds, like the craziness that you see in OpenAI, etc. And well, that can be a problem, right? There's compute is really important. DeepSeek now might imply for some people, oh, maybe compute is not so important, but that would be the wrong lesson to learn. We need to see how exactly the numbers add up, or whether the $5 million that are reported for coming up with DeepSeek, whether that is really from scratch or whether it was started from a llama model or whatnot. We don't quite know. And even if it was from scratch, TabPFN was trained from scratch on 8 GPUs that are 5 years old. But on the other hand, we did have 200 GPUs in order to do the research around it. And so this factor of 15, that I would easily put that on top of the DeepSeek model. So then you're already at sort of, in the range of 100 million. And sort of 100 million. If we had 100 million GPU hours, then we could also train a model like DeepSeek, I'm very sure. And actually, we have this initiative also on OpenURL with the Alice Institute that is going to try exactly that if we get compute time. And if we get compute time for tabular foundation models, then we can also build something that's great. So there's also opportunities for public-private relationships there in order to do research in the open that then goes into commercial applications, etc.
Frank, thank you very much. It was a great time. Great to hear from the horse's mouth, everything on tabular data. We wish you're going to be a multi-billion company soon, if I understand what you wish.
Yeah.
Until then, listeners, we said that want to get in touch with you can do so by LinkedIn. We're going to share all the links. GitHub, these days, it's all so easy. You're looking for the company name GitHub. Otherwise, if you, the listener, have any question, comment, as always, please send a short email to me, peter@aipod.de. Very happy that you stay with us so far. Looking forward to have you with us again. And Frank, thank you very much for your time and good luck with your company.
Thank you so much, Peter, and thanks a lot to the listeners. Hopefully, I'll be welcoming some of you into the TabPFN community. Thank you.
Thanks, Frank. Bye-bye.
Bye-bye.